Okay, so today we're going to start talking about realistic situations that can be described by quadratic functions. So we're going to sort of steer away from random patterns and boxes, and those of you who are struggling with that are going to find it's a blessed relief, hopefully, from that. So one thing that is very easy to model with quadratic functions is like gravity or falling objects. It's a very typical example, very standard example. Just because of the way gravity works and like falling objects and the way their speeds increase and decrease can all be modeled quadratically. So a rock is dropped from the top of a 500-foot tall building. A camera captures the distance the rock traveled in feet after each second. So to start, it's at 0 feet, and at 1 second it's at 16 feet, 2 seconds, 64 feet. So this is measuring the distance it has fallen. So I want you to take a minute and think, what do you notice about all of these numbers? Like, what do you notice about 0 and 16, 64? Is there anything in common with all these numbers? Anything in common? Well, the first thing I notice is that 16 and 64 are both perfect squares. Like, I noticed that 16 is 4 squared and 64 is 8 squared. But another thing to notice is they're all multiples of 4. Like 16 is 4 times 4, 64 is a multiple of 4. They're all even, they're all multiples of 4. We'll see if that comes into play. So that's a good thing to notice. If you look at part A, how far will the rock have fallen after 6 seconds? Well, let's see if we can notice some growth patterns here. See if you can figure out how far has the rock fallen after 6 seconds. Where will it be? And don't just say like, well, all right, the ground's there. It's probably hit the ground by then. Yes, but assuming the ground wasn't there, where would the rock be? Okay, so I tried to do some math here, and I was like, well, all right. It goes down 16 feet the first second, 48 feet the second, 80 feet, 80 more feet in the third second, 112 feet in the next second, and 144 feet in the next second, which doesn't really seem like there's a good pattern there, but there actually is one that I'm covering up right now. And I said, well, what if there's a growth factor? Is it exponential? So I divided 64 by 16, and I got 4. And I divided 144 by 64 and got 2.25. So no, there's no growth factor. So it's not exponential. So let's look at what I did here. Here I noticed that every second, it falls 32 more feet. All right. So maybe that'll help us. How much will it fall in the next second if it falls 32 more seconds? Well, 144 plus 32 is 176. So I'm going to go ahead and say 400 plus 176 is 576 feet. So now let's see. Angelica noticed something different than I did. She noticed that all the distances fallen are multiples of 16. I said multiples of 4. She says they're all actually multiples of 16. And here's the interesting part. She says 16 is 16 times 1. 64 is 16 times 4. 144 is 16 times 9. 256 is 16 times 16. 416 times 25. And let's just see what 576 is. 576, you can have a prediction ready, is 16 times, let's see, 576 divided by 16 is 36. So what do you think? What's the relationship between 1, 4, 9, 16, 25, 36? Well, they're all 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, which is the number of seconds. Pretty cool, huh? So, no. Okay, so we're going to use that to predict the distance after 7 seconds. And yes, assume the building's tall enough that an object dropped will continue to fall for at least 7 seconds. Suppose the Empire State Building or something, and you can actually drop something off that building. Which turns out in most cases you couldn't because of the shape of the building. It wouldn't reach the ground before hitting some other part of the building. Anyway, assume you could drop for 7 seconds. How might we figure that out? So if we continue this pattern, like 16 times 5 squared, 16 times 6 squared, 16 times 7 squared for 7 seconds, we get 784 feet. So what rule are we really using here? What equation could we write with d representing the distance dropped after t seconds? D equals 16 times, well, the number of seconds I have squared. That was my rule that I came up with. I notice it's quadratic because it has something squared. All right. And just to go back to our rule from earlier, if I add 32 to this, I'm really going up by, let's see, I'm adding 208, and 576 plus 208 gets me 784 feet. So it still works up there, 784 and 784. That same rule still works. Pretty nice, huh? So it turns out that Galileo Galilei, the Italian scientist, is actually the person who came up with the relationship that the distance that objects fall as a function of time, seconds, is actually 16 times t squared. And that's actually a very common physics formula when you get to physics, 16 t squared if you're using feet. If you use meters, there's a different formula. But if you use feet in seconds, this is your formula, the distance of how something goes. And it works pretty much for free-falling objects where the only force acting on them is gravity. See, forces too, just like science class. So if an object is dropped from 576 feet, we could figure out how far it falls in half a second. So in half a second, how far does it fall? Use the formula to figure that out. So it's just a matter of using our formula. Half a second squared is a quarter, so 16 times 0.25 is 4 feet. So then on my table down here, after half a second's fallen 4 feet. 1 second was 16 feet. So you want to fill in the rest of that table. And then here we notice it started at 576 feet. So to start, it's 576 feet off the ground. And after half a second, it's 576 minus 4, which gets me 572 feet. And here we're at 576 minus 16. We see the pattern happening, right? And, oh, Diego and Elena, you're not members of my class. Whatever. Okay, so fill out the rest of those tables. Think, how are they alike? How are they different? Like, what's the significance? Like, what does Elena's table show? And then what does Diego's table show? Because they both have two different purposes. And completing it, okay, that was pretty much what I already told you to do. So give that a try real quick. Okay, so there we go with our tables. Not too bad. We're just plugging in the t-values here, doing the math. This is my formula. And then doing 576 minus that. 576 minus 36 gets me 540. So then 576 minus 16 t squares gets me my distance from the ground. So Elena's shows distance fallen, and Diego's shows distance off the ground, or it shows like height. All right, so there's their differences. So try one more thing before we do our practice exercise. All right, this type of problem I would give you to do in class. And just say, like, do it. You can do it. It's not too bad. So I'm going to just sort of walk through a little bit of it, and then I'll just post the answer to it at the end of the video with no explanation. So make sure you ask me questions on it if you don't know where it came from. So the baseball travels d meters, t seconds, being thrown from the top of the building. So even if it's thrown, it can still be modeled quadratically, just with a different number. All right. And notice we're doing meters this time, not feet, so that's why it's not 16. So, complete the table and plot the data that you came up with. And plugging in your seconds and then just plotting the ordered pairs. Your ordered pairs are t comma d's, not x comma y's. All right, answer the questions. Shouldn't be too crazy. Let's see. So, make sure there's no tricks coming at you here. Yes. You could probably manage all this stuff. All right, I'm going to show you everything once you've done it. So pause the video and do all the math before I show you what the answers are. All right? All right, here we go. Here's what you should have gotten. No, in the first second it went 5 meters. Then the second it went 15 meters. Could use any 2 different points there. Here's your formula. All right? So remember, quadratics often refer to fallen objects. And when you are thinking about what makes an equation quadratic, it has to have a square in it. And when you're thinking about, like, is a table representing a quadratic equation, you think about, well, that first distance isn't necessarily anything, but the differences of differences should be the same. All right, then in this case, maybe it isn't. Hold on. Sorry, yes it is. I panicked that it wasn't going to work. So if you take the differences, every time it's getting 2.5 higher. Plus 2.5, plus 2.5, plus 2.5. So that's one way to distinguish if it's quadratic just based on a table. Are the differences of the differences the same? Or does it seem to follow that nonlinear pattern? All right, so hopefully that helps. And best of luck today.